In this video, we're going to look at what differential equations really are, maybe talk about some of their basic properties, and maybe even solve one or two differential equations, right? So let's start with a definition. So a differential equation is an equation that involves at least one derivative of an unknown function, right? That's what a differential equation is. So it's an equation, and we know what equations look like. But the key now is that these equations involve at least one derivative of some unknown function. And what is the goal? What are we looking for in these equations? So the goal is to solve for this unknown function. Right? It's to solve for this unknown function. So let's really think about what this means. So we're used to equations that look, like this, for instance. Equations that look like this. Equations that look like that. Equations that look like that. And all of these equations, these are either algebraic or transcendental equations, right? So these are algebraic or transcendental equations. And they're all different. They're all different. You solve them in different ways. For instance, this one you may try to factor or use the quadratic formula. Here you might use the inverse function of your natural log. And you might get, so like this equation probably has two solutions. This equation can only have one. This equation has infinitely many. But the one thing that they have in common is that all these equations, when solved, they produce real numbers, right? Or I should say just numbers in general. So when solved, so let's say this, so the solution of all of these is some set of numbers. Right, so the solution is a set of numbers. When we solve a differential equation, we're not solving for a number, but instead we're solving for a function. Right? So what do they look like? Well, you've actually seen differential equations before, right? In fact, going all the way back to your first semester of calculus. So here are some examples of differential equations. Right, some of which you've seen, some of which you might not have seen. Let me write this as dy dx. So something like this. This is an example of a differential equation, right? So there is some function out there, y, that when I differentiate it, I'll get, with respect to x, I'll get x squared plus 4x plus 2, right? So this is an example. Do you know how to solve this? Well, maybe in a little bit we'll brush up on some basic calculus and come up with a solution for this. But this is an example of a differential equation. Here's another differential equation. It might be something like this, right? So this is saying that there is some function out there, x which is implied to be a function of t, and when I take the derivative of x with respect to t, and then I minus a function x, I will get 0, right? And these differential equations, they only involve a first derivative. But as we know, you could have second order derivatives, third order, you can have higher order derivatives. So here are some examples like that. We might see a differential equation like this. Let's see, dy dx, and then plus y squared, that's equal to e to the x. So this is saying there is some function that when I differentiate it twice, and I subtract the first derivative, and then I add the square of the original function, I'm going to get e to the x. Again, I don't know what that function is, but that's what this equation implies. It's the idea that there is some function that when I perform these operations here on the left, then I end up getting whatever is on the right. So if we could somehow figure out that what y is equal to, then we would end up finding a solution to this differential equation, and that would be true for all of these, right? Now, some differential equations are easier to solve than others, just like how there's certain equations that are easier to solve than others, right? And as we go through them, we'll look at different techniques, and we'll have different levels of difficulty in terms of coming up with the solution, right? Now, one of the big things in differential equations, it depends on you recognizing first what type of equation it is, and then deciding based on the type of differential equation, figuring out, okay, well, what's the best, or maybe what's the only method of solution that applies. So one of the things you do pretty much at the start of the study of differential equations is you want to classify the differential equations in different ways, right? So we're going to look at a few ways that differential equations can be classified. So let's say classifying, and I'll just use DE as an abbreviation for differential equations, right? Now, the first big classification is based on whether you have an ordinary differential equation or a partial differential equation, right? So I'm going to break it up like this. And we're going to have ordinary versus partial. In an ordinary differential equation, the goal is to find a function that is a function of one variable, right? So in an ordinary differential equation, the unknown function is a function. So it is a function of a single variable, right? And these are the functions that you are most familiar with, particularly thinking back to your intro to calculus, and even before that in algebra and trigonometry. So in other words, you'd be solving for functions like y equals f of x, right? Or x equals g of t, or s equals h of p, right? So anytime you write something like this, what you're saying is that this variable, or this dependent variable on this side is a function of this independent variable, right? So on this side, it implies the dependent variable And then on this side, the x, the t, the p, these would represent independent variables. And in an ordinary differential equation, you can only have one of these, right? One independent variable. In a partial differential equation, it's still you have one dependent, but then you could have multiple independent variables. So over here, when you learn about partial differential equations and you learn how to solve them, what you're going to end up with are you're going to have that the unknown function that you're solving for. So the unknown function is a function of at least two variables, and meaning two independent, at least two independent variables. Right? And for those of you who have taken multivariable calculus, you know about partial derivatives and you know all the different notations and you know what those functions look like. So again, this is not something that we're going to talk about in this course, but it has to be mentioned in the context of how you classify them, right? So like, in this course, we're just going to focus on the ordinary ones, right? But even within the ordinary, there are lots of other ways of classifying, and we're going to look at those shortly. But in a partial differential equation, you might have something like this, where your z is a function of x and y, right? So you might see something like this. Or you might have that w is a function of x, y, and z, where this is implying that my dependent variable w depends on these three independent variables, right? And then you could have more. You could have something like this. Q is a function of x1, x2, x3, x4, x5. You could have functions like this, where your function q depends on these five independent variables, right? So, just looking at this, it just looks more complicated. And yes, partial differential equations in general are harder. You need more multivariable calculus, you need more linear algebra, you need a lot of stuff to be able to analyze these. And this is the only time we're going to mention partial differential equations. Typically, you learn about ordinary differential equations, maybe take one or two courses, and then you move into partial differential equations, right? Okay, so that's the first big layer of classification. Is it an ordinary differential equation? Is it a partial? Now you basically can tell um, uh, based on the derivatives that are in there. So if you know what a partial derivative looks like, you would recognize it. An ordinary derivative are like the derivatives that I wrote earlier, the dy dx or the dx dt or all the different notations, your f prime, things like that, right? So that's the first layer of classification. Now, in the ordinary, well, actually in both, but again, we're just going to focus on this. Another category of classification is called the order of the differential equation, right? So the order of the dE is the order. I know this sounds weird that the order is the order, but hold on, it's the order of the highest derivative present. So the highest derivative present in the differential equation, right? So in other words, as I was saying earlier, you have some equations that only have a first derivative. Those would be called first order. Some differential equations might have just two, like up to a second derivative, and those would be second order. So you look at the differential equation, apply what we know about the notation for derivatives, and then decide, is this first, is this second, and so forth, right? So here are a couple examples. So something like dy dx plus y is equal to the sine of x, right? So in this case, we would say that our dependent variable is y. Our independent variable well, again, in an ordinary differential equation, you're only going to have two variables. You know, you're going to have one, which is dependent, and the other, which has to be independent, right? And in this case, we could say that the order, well, there's only a first derivative. So you could say it multiple ways. You could say it's of order 1, or you could say it's a first order. So I'm just going to say that the order of this differential equation is 1, right? Let's take a look at another example and again identify these three key things: the dependent, the independent, and the order. All right, so let's take a look at this. So if we have d2 dp over dt squared all to the third power, and then plus the square root of dp dt, and that's equal to t squared plus 1. Right, so this one looks a little bit more complicated, right? And again, our focus right now is not solving, right? We'll have lots of time to solve, but right now we're just getting used to what these look like, and then we're getting used to identifying key characteristics or properties of the differential equation. So based on this, I can say that the dependent variable is p. Right, so our dependent variable is p, and then our independent variable is t. Right, so here p would be a function of t. So our independent variable is t. Now for the order, and this is where you have to be careful, particularly when you're using like the Leibniz notation for your derivative, right? Here, this is saying that we're taking the second derivative of p with respect to t, right? And then this 3 is interpreted as a power, right? So this is not a derivative, right? The highest derivative in this entire equation is a second derivative. So this one is of order 2, right? So this one is of order 2. So don't confuse an order like let's say, so this is a second derivative. Don't confuse it with the third power. Right, so this is saying you differentiate twice, and then whatever that second derivative is, you raise it to the third power. And the rest of it is kind of irrelevant as far as the classifying, right? Because this, again, is still just confirming that p is a function of t, and we're taking the square root of the first derivative. But as far as identifying the order, we always look for the highest, right? Just a couple other things in terms of notation. So I've been using the Leibniz notation all the way through, but then obviously we can use primes, right? So you might have something like this that indicate a third derivative. Now, if I don't write anything else, it's like, well, what is the independent variable? Because this is saying we're differentiating y 3 times, but I don't see with respect to anything else. So let's say this is all you see. You know, what if that's all you see and that's equal to 0, right? It's hard to tell. We would kind of have to make an assumption, and it wouldn't be an unreasonable assumption if you assumed that the independent variable is x, right? We typically would, you know, favorite pair of variables, right? It's y as a function of x, right? Otherwise, if it was supposed to be really clear what the independent variable is, and if it was different from x, it would be indicated somewhere in the equation. In other words, it might be indicated like this. Right? You might see something like this, then it becomes very, very clear what the independent variable is. Right? And we can only have two variables in a single ordinary differential equation. Right? So this one, again, it's clear that the y is dependent. Now r is the independent variable, and this one goes up to a third derivative, right? So this would be order 3, or you can say third order, different ways to say it, right? Now, when the order gets to be pretty high, writing these primes is not the most, at the very least, it's not very aesthetically pleasing. It doesn't print well on a page. So typically, like once you get to 3 and 4 and 5, you might see something like this. So you might see a 3, but then in parentheses. And that 3 is interpreted differently than this 3. This 3 in the parentheses now indicates that it's a third derivative. And let's say it's like this, right? Now, having, a second derivative with two little primes there, that's fine. I mean, we could do that. Right? And sometimes in equations you'll just see that it abruptly changes from the primes, and then it's replaced by a number but in parentheses, and so forth. And let's just say this is like t cubed, right? So something like this, your p is your dependent variable, your t is your independent variable, and then the order is still 3, or third order, right? One more notation about one more word about the notation. Whenever you have an independent variable of t, so if your derivative is with respect to t, there's an alternative way that you can define this, right? And, let me finish writing the order, right? So, we have two typical ways that we write derivatives, with primes and with the d's. Let's say like that. So let me do that, right? So these both say the same thing. Well, when you have a derivative with respect to t, and if t represents time, you have another notation that's called a dot notation, or a dot derivative. So for instance, I'm going to rewrite this equation, since it is a t derivative, or with respect to t. This third derivative can be denoted as a p with 3 little dots on top of it. Sometimes it's even called like fly speck notation. I have no idea why. But this, and then this, and then this equation is saying the exact same thing here, right? And even if, for instance, there wasn't like a t in here, if this were just, let's say, 0, for instance, then the use of the dot notation implies that the independent variable is t. So anytime you see a dot above a variable like this, it indicates a derivative with respect to t. And the number of dots would represent the order, right? So basically, anytime you have something like, so let me just say, like the dot notation, say it over here. So the dot notation is always with respect to t. It's always a what we call a time derivative. And you use it a lot in courses like dynamics. You do a lot of you hear x dot, x double dot, and so forth instead of x prime and x double prime, right? So that's just some of the notational issues, right? So in terms of solving, and that's obviously a big part of this course, not just being able to identify, but I think we could sort of wrap up this video by showing you that we've already solved differential equations, right? And even there are times in a multivariable calculus class where I would mention the word or the phrase differential equation as soon as you learn about antiderivatives, right? As soon as you learn about antiderivatives, I think that's a good time to introduce that terminology. So here's an example, right? And we could even we could go back to that one that I wrote down, but let me just write down another one that's a little simpler. So let's say I have that the dy dx is equal to x squared, right? And I want to figure out what the solution is, right? Well, this one is so simple. It's simple because the derivative only depends on the independent variable, right? So this only depends on the independent variable x. Right, our independent variable x. So what we learn about in calculus is if I know the derivative and I want to figure out what the original function is, then I take an antiderivative, right? And I can take the antiderivative because I can integrate this function with respect to x. Another way to think about it is I can do this, I can write this derivative in differential form, right? You might remember that, where you take the derivative over, the dx over, sorry, and multiply the right-hand side. So this is telling me the same information as this, right? And I know the way I can go back from a differential to a function is by integrating. So I can integrate both sides, right? And that's a really good way to think about it. So on the right-hand side, we take the antiderivative of dy, which is just going to give me y. And then on the right-hand side, or did I say left-hand side? Well, on the left-hand side, we integrate our differential y. That gives us y. On the right-hand side, we integrate x squared with respect to x. And with our power rule, we'll get 1/3 x cubed plus c, right? And this function, but see the thing is, even the terminology that we use, in the intro calc classes, it's not super precise because like when we say the antiderivative, the word the implies it's the only one. But actually, this is a whole set of functions, right? Because we know that this constant could be anything, right? So this is actually referred to as the general solution of this dE, right? In other words, it's all the possible functions that if I were to differentiate them with respect to x, I would get x squared, right? So this is the general solution. Not only that, we are able, you notice we have the dependent variable isolated on one side, and then we have the function of x on the other side. So whenever you have your dependent variable being expressed as a function solely of your independent variable, so in other words, you only have the independent variable on this side. This is not a variable. This is more like a parameter, or actually a free variable, right? But here's our independent variable. This type of equation is called an explicit equation, right? So this is the explicit general solution. And it's explicit because we have the dependent variable expressed as a function of the independent variable. It's not always possible to have it in this form. It's not always possible to get your solution in this form, assuming that y is dependent on x. But when we do, we say we have an explicit solution, right? Now, there is one way that you can sort of visualize this, just to emphasize that this in fact represents several, in fact, infinitely many functions. And the way you can see it is, if I think about like the graph of 1/3 x cubed, if I graph this, and let's say I use that terminology from algebra where you use it as your parent function. Well, y equals 1/3 x cubed, it has a basic shape like this, right? And then, well, how do we visualize this plus c where we don't even know what plus c is? But think about it as a translation of your graph. By adding a constant to your parent function, you shift that function either up or down depending whether the constant is negative or positive. So for instance, if I were to add 1 to this, then I would shift this graph up 1 unit, and then that would change the y-intercept, but it would have the exact same slope. So it's like the curves would be parallel. Instead of saying parallel lines, this general solution actually represents parallel curves. If I add another one, then again, I know mine's not super parallel, but you can get the sense of just shifting the graph up. If I subtract 1, then the graph moves down 1 unit, and then it looks like this. So I get a whole bunch of these, right? And all of these depend on the constant c, right? But suppose I wanted to know exactly, so let's say, let me draw another, well actually, let's say I wanted to find the specific one now that passes through the point, let's say that point right there is the point 0, 3/2, right? Suppose I wanted to find, of all these parallel curves, which is the specific curve that passes through that particular point. So then we can use that information to figure out what the constant is, right? So let's go ahead and do that. So if the curve passes through the point 0, 3/2, this information is telling me that when x is equal to 0, my independent variable is equal to 0, my y, which is my dependent variable, has a value of 3/2. And then that leads to a certain equation, right? So I can plug 3/2 in for y, 0 in for x, and then what I have is a simple equation to solve for c. And this one works out really nicely. The c ends up being the 3/2. But again, I wouldn't like circle this. This is not my answer because this is not the function, right? Always keep reminding yourself that when you're solving a differential equation, it's a function that you're coming up with. So what we've done there, we've simply identified what the constant is. So of all these parallel curves, the one that passes through the point 0, 3/2 is this one, 1/3 x cubed plus 3/2. And this is called a particular solution. The particular solution that satisfies this condition, right? So this is called the particular solution satisfying the condition right? That this point defines. So the condition, and you can write it several ways. You could write it as the ordered pair, or you could write it as like y of 0 is equal to 3 halves, right? And again, if we think about it as, if we think about these as parallel curves, then this is the only one. This is the only function that would satisfy my original differential equation, and it also passes through this particular point. And that's why, again, we use the word particular. So general represents infinitely many functions that satisfy the differential equation. Particular implies one of those many functions, right, that satisfy a certain condition. Now, you might have some differential equations where even when you specify a specific condition, you might still end up with multiple solutions, and that could happen, right? In fact, and then there are some times when you specify a condition, you can't find a solution, right? You might not be able to find a C that would satisfy the constraints that are put in place by the x and the y value in your condition, right? So there are all these little things that can happen with differential equations. And as we get started on this journey, we will encounter many of them along the way, right? So hopefully that intro kind of sets the stage. And then in the next video, we're going to jump right into further classification and other methods of solution. So I know you can't wait to see, and I can't wait to show you. See you then.